All right, so just a sample problem to start you off with. We have a binary search tree here, and this is the test tree that we have down here. And I want to know, when I run traverse on this test tree, what's the contents of the list? So take a couple minutes and think about it. If you're a fast typer, of course, you could just type it into Racket and get the answer. If you don't want to do that, draw the tree and then trace through what's happening in the code on the tree. Does anybody have any ideas to what list is going to be produced? Any thoughts at all? Yeah. It is a map to get down through the tree, but what order is it going to be in? So it's a little tricky to see here, so I'll tell you what it is. If we run this particular piece of code on our binary search tree, which let's actually draw the tree out here so you can see what it is. We've got 5, 2, 1, 3, 7, 6, 8. There's our tree. This tree, with this particular function called traverse, is going to create a list like this. Or I guess there's no 4. I forgot the number 4. This traverse function, traverse means to visit each node of a tree exactly once. This traverse function is known as an in-order traversal. If you have a binary search tree and you do an in-order traversal, you get a sorted list, which means that you can use a binary search tree and an in-order traversal to sort a list of things. What you would do is you take your unsorted list of things and you one by one insert them into a binary search tree. Once you've created the binary search tree, you then call in-order traversal and you get the sorted output, which is kind of cool. And if that binary search tree is a balanced binary search tree, i.e. it's an Eval tree, then this would take big O of n log n, which for a comparison-based sort, that's the best you can do. So you can use this for sorting. All right, then, if you have a clicker, you should get it out. And if you don't, you can sit there and you can pretend or something. I don't know. So I'll give you a minute for this one. I'm going to admit that I wrote this question while watching Independence Day, so hence the alien influence. All right, if there anyone who has not pushed a button, push it now or forever hold your peace, because I'm shutting it down. All right. Wow. Does like everyone in this class like attend or get the answers from the previous section? Because I swear, like it's almost like 100% for clicker scores in this section. I'm like much lower in the 1 o'clock. Oh wow. Yeah. Oh, I'm just trying to figure out because it's like there's such a disparity in the marks between the two. It's crazy. Maybe you're just so. Maybe you study more.
To pass.
Anyways, obviously B is the right answer. Mutual recursion is when you have function A calling function B and B calling function A. So it makes this nice big old loop. It's very easy to believe that any recursion involving trees is mutual recursion, but it's not, because I can implement a literal shit ton of functions that are recursive on a tree and don't involve mutual recursion at all. Because if you can avoid mutual recursion, you probably should, because it's exceptionally confusing compared to just plain old recursion. All right. So, another one. Let's see what you remember about binary search trees. For all I know, the reason why you guys always get 100% and there's some secret Discord server somewhere where people are posting the answers. Which, for the record, I couldn't care less. All right, you got like 2 seconds before I push the end on this. All right. C is the answer. It's one of those things you got to remember, and it's confusing about a binary search tree, but if you get it wrong, then you have a tree in the wrong order. Binary search tree, as per our definition, everything in the left subtree is smaller than the node, and everything in the right subtree is bigger than the node. All right, one more question, but you only get like 30 seconds to answer it. And I gotta ask it because like it's tradition for like students to go on Reddit after a midterm and have like a crying thread. There was no thread. I was like deprived of this like post-exam entertainment. I suppose I'll just have to wait till my midterm on Thursday night because I'm sure they're gonna have one. All right. Now, I kind of believe E because there was like the highest percentage of DNWs I think I've ever seen. So either a whole bunch of people forgot this course had a midterm, or everybody has coronavirus. I don't know, whatever. All right. This, by the way, agrees with what the 1 o'clock section said. They also, a large people forgot they had a midterm, and a lot of people felt that was fair, which I assume when there's no Reddit thread, it's like I'm sitting there, it's like, what did they think about it? Was it too easy? Was it too hard? I don't know. I'm bored. So I kind of assumed that you just didn't have an opinion on it. All right, now on the topic of the midterm, we are grading it right now. It's almost done. I think that we're just waiting on the question that I'm supposed to mark. Roger's nodding his head enthusiastically because he means it's something that he doesn't have to do. Yes, you wrote it last night, and everything except for my question is marked.
What? What?
How? Because we have an army of TAs that's like 6 people who sit there in a room and they grade it all day. And we feed them candy and donuts. So, all right, settle down, settle down. What you should anticipate is that sometime in the next 36 hours, these marks will get released to you. You are going to have to wait for me to finish the question I'm grading. Once all of the exams are graded, which will be tonight, I have to look at the scores, and if the midterm average is like 40, I'm obviously going to like change it. If it's a high average, we won't change it, obviously, because that's just cruel and unusual punishment. But we do need to look at the scores before we actually decide to release the marks. They should be released to you probably by Thursday, though. That's the hope. I don't see why it would be any later than that. When they get released to you, you will also get the solutions to the midterm, which, keep in mind, the solutions will be the solutions I wrote at like 4 in the morning some night.
So there were mistakes?
No, because we had our lovely TAs actually check them. So keep in mind that you are not, for a lot of the questions, being purely judged, did you get the exact solution that I give? There's some flexibility in there, and we've actually been a lot more flexible than we probably should be. So for example, I know there's some functions that were forbidden according to the EULA at the front of the exam, which nobody reads, like including myself. No. And we kind of let a lot of that stuff fly. But so our TAs in our ISAs, they've been working with this course for a long time. And any question where we felt there could be a variety of different answers, I had them mark that so that they could actually read your solution and determine whether it actually worked or not. So it's not just, did you get my exact solution? We're actually going to read through it. Now, we're not going to take your code and put it into Racket. So if you wrote something that was like 10 pages long, chances are we moved on. But we'll go, yeah. Question? That's probable.
Yeah. Other question. If we say our answer is wrong and it's 10 pages, we ask
for a remark?
Look at it again.
Yeah. It's just during the process of grading like 133 papers, we didn't want to sit there for 2 hours reading it. There's 133 papers. Yeah. Yeah. I can't answer that until I actually see the results. So if I see the results and the overall exam strategy was really, like the overall exam grade was really low, then what I would normally do is I would look and see if there are particular questions where everybody like did really badly on. I can think of 2 off the top of my head. One of them is the one I'm marking. That's 2C.
Oh.
2C was the question about the code not being general or reusable.
I hated that question so much. Yeah, me too.
Well, every question on the midterm can't be your favorite question, all right? Some of them have to be a little bit tricky. But that being, like, I will look over the grades, and if there's one question, I may remark the whole set. I've done that before. or I may adjust the exam as a whole. I really can't say what we're going to do until we actually have the final grades tabulated, which is relying completely on me to actually finish it.
Good luck.
Well, it's kind of hard to do that when I'm like, right here right now, right?
How do students decide?
Well, I mean, I could get you to mark each other's exam, but that's not a good idea.
I totally have to do something.
All right. Anyways, any other questions? I know you haven't seen your midterm, but we were pretty chill, by the way. I kind of applied our CS135 grading policy, which is be pretty chill, with the exception of the stepping question. That's not chill. But other than that, we'll see what happens. All right, then. Let's move on from that. You will, by the way, we'll put remark instructions and all that on the piazza, and you'll have an opportunity to do a remark request. Please don't overburden poor Roger over there, though. He's got to work on passing 240, so. But to be fair, so 240 gets easier from here. Proofs are all at the front, easy crap's all at the end. All right, so we left off, we were talking about these evolution tree things, which I said, for those of you who are actual science people and know what evolution is, please forgive our gross misrepresentation of this. But we have this mixed data type called an evolution tree. And I'll go back here somewhat. And our evolution tree is either a current species, which is going to be our leaf node, or an ancestor, which is going to be an internal node. And if you're an ancestor, we're going to make the assumption that when some evolutionary event happened, like a meteor fell from the sky, you evolved into exactly 2 species. Again, a simplification of things. I'm not a biology person. All right, so our Evo tree is either a current species or an ancestor, so it's either a leaf or an internal node. We have a mixed data type, which means that our template for an evolution tree is going to have to take into consideration there are 2 different types of nodes. So if we are a current node, then we run the current template. If we're an ancestor node, we run the ancestor template. Now, just like the data definition, which is mutually recursive, our template is also going to be mutually recursive because the template should model the data definition. So if your data definition has no recursion, then your template shouldn't have recursion either. If your data definition does have recursion, then so should your template. This template here, or this data definition has mutual recursion, which means that your template should also have it. So in our current template, we're going to do something with the name fields and something with the endangered field. If you're an ancestor, then, well, this one isn't quite right, but this template is. We do something with the name, something with the age, and then we're going to call the evolution template on the left and the evolution template on the right, because the left and right child of the ancestor are evolution tree types. So we have the mutual recursion going on here. And we ended off last class, we were implementing a function to count how many leaves were in this tree. So how many current species actually exist. So in order to do that, if we're going to take our mutual recursion template and we're going to rename it and fill it in. And essentially what we need to do is, if you're a current node, they have it calling a function here. There's no actual reason to call a function here. You should just put 1. Because otherwise, by the way, every time you call a function, you're wasting the CPU's time. So, there was no reason here to do that. Let's just put a 1 here. And then if you're an ancestor, we're going to count the number of leaves that there are in that node. So the number of leaves for that amongst the children. So if we look at the function for counting the ancestor, what we're going to do is to count the total number of children, or not children, the total number of leaves. It's equal to the sum of the number of leaves in the left subtree and the sum of the number of leaves in the right subtree. And to compute the number of leaves in the left and right subtree, we call that other function that called us. So it's the mutual recursion function. We're going around in a nice circle. All right. So we've talked about traversal a minute ago, but just to reiterate, when you traverse a tree, you are visiting each node in a tree exactly once. And there are three primary ways that you can traverse a tree. There is post-order traversal, there's in-order traversal, and there's pre-order traversal. And it's just what order do you visit the nodes in. So things like post-order, that would be doing things like visiting the children before the parent. And in order would be actually putting things out in the order that they're specified. We don't really cover that topic at this point, but if you're interested to know more about post, pre, and in-order traversals, the Wikipedia page is pretty great. I recommend that you read it, actually. All right, so what I want to do with my evolution tree is I would actually like to traverse this tree and visit each and every single node and produce a list. And that list should contain all of the names of all of the species in the evolution tree. Now, we haven't specified what order to do that in. And because we haven't specified what order to do that in, there's actually a lot of different solutions. So, we'll call this function list the names because we want to list the names of all the species. And we're going to start by taking our mutual recursion template and just plopping it down here and renaming them. So now what we have to do, if I want to list all of the names of all of the species in my tree, then I need to add myself, my name, to a list of all the names I find in my left subtree and the list of all my names in my right subtree. So if the node is current, well, that's the base case and I just produce my name. And otherwise, if I'm an ancestor, well, that's when I'm going to need to figure out some way of combining the results for myself with the results from the left subtree and the right subtree. And as I said, there's lots of different ways that you could do this. Now, the way that they've selected to show you this in the notes is actually using accumulative recursion. You can use accumulative recursion for this. So we have our wrapper function. Now, our result is supposed to be a list of all of the names of the species in the tree. So our accumulator should start out as an empty list because we're accumulating the names. Then our actual accumulative recursive function is going to be the one that maps to our main template. So if it is a current species, we are still going to, we're going to call this function here, list C names, that's going to do something. We aren't going to produce the name. We're going to do something with the name of this node and the accumulator. And otherwise, if we are an ancestor, then we are going to do something with this node and the accumulator as well. So this is really just figuring out what helper function do I need to call based on what kind of node this is. Now, if this is a current species, what we're going to do is we take the names, the accumulator. Names is going to include every species name that we've seen so far. And what we're going to do is we are actually going to append ourselves to the front of it. So we're adding ourselves to the accumulator and returning that list. So if the list is empty, then it's just us in the list. If, however, we are an ancestor node, this is where it gets kind of complicated. We want to produce a list that contains us along with all of the names of all of the species of our left and right subchildren. So I'm going to cons myself onto getting the names from my left subtree. What about getting the names from my right subtree? Well, I could append the results from my left subtree to the results of my right subtree, but I'm using accumulative recursion here. So what I'm going to do is my accumulator is going to be the results of getting all the species named from my right subtree. So you can actually have your accumulator be produced from a recursive call itself. This is an ugly, ugly solution. I do not like this answer. It's really ugly. It works, but I don't like it. It's hard to think about. The reason why I say that this function is rather ugly is because seeing what's going on with the accumulator, figuring out what result we are accumulating, is tricky. There's a simpler answer to this problem, and it doesn't even involve mutual recursion. Obviously, I'm not going to leave you in suspense. I will actually show it to you. And it is, not that one, not that one. Here it is, right here. There we go. A single function with no mutual recursion traverses every node in the tree. No accumulation, quite simple. Let me explain how this works. So, if the tree is empty, I produce empty because that's a base case. There's no nodes. If this is a current node, then I produce a list containing the name of the current node. If this is an ancestor, then I'm going to cons my name onto the list produced by appending all of the species names from my left subtree onto a list containing all the names from my right subtree. Done. I like this one better, by the way. Both of them work. Both of them work. I believe, if memory serves me, they don't give you the same order of traversal, but they both work. Maybe the accumulative recursion one speaks to you. This is the one that pops into my head. This is very simple. Now, you wouldn't be able to do this if you didn't have access to a pen. So this function here actually relies on the existence of a pen. If you didn't have that, you'd have a problem. Lots of ways to traverse the tree, though. All right, any questions about this traversal stuff? By the way, there are more solutions. There's lots more. My personal take on things, by the way, is unless we explicitly tell you to do something with mutual recursion, if you can come up with a very simple recursive solution for something that doesn't break any of the rules and is like only 5 or 6 lines of code as compared to like having 3 or 4 different functions, you should probably use the simple solution. The problem with mutual recursion is that it's actually quite tricky to think about. Very tricky. So, because I know you've just finished your midterm, finals are a month away. You should start studying for them, right? You know, you gotta like pass the weighted average of the midterm and final of this course to pass the whole course, so you gotta pass that final. They've given you some sample problems to try for Evo trees. These are things that you don't necessarily have to do with an evolution tree. You can do them on any kind of tree if you want. Some other sample problems that you might try are go online, look at the wiki page for pre, post, and in-order traversals, and then for a binary search tree, implement all 3, just so you can see what is the order that these 3 different traversal methods actually produce the nodes in. So there's lots of different tree sample problems that you can actually do. All right. Evolution trees are boring. This is a math building. We should do math, right? So, how about trees representing binary expressions? That's actually somewhat useful. So, a binary expression is any math expression that has exactly 2 arguments. So, add, multiply, divide, and subtract all have 2 arguments. And if you take a binary expression, you can actually turn it into a tree, a binary tree. So we have this expression here. We have divide, and it has a left and right argument. And then add has a left and right argument. Multiply has a left and right argument. And we've actually gone and turned this into this beautiful tree here. Now we could take any expression that involves these binary operations, and we can do the same thing to it. So we could have the following one. Just gotta remember what I wrote here. So if we have this expression here, we can turn this one into a binary expression tree as well. We start with the plus, because there's our left and there's our right. There we go. Now, one of the things I want to point out to you is that I've kind of drawn the binary expression tree a little bit differently from how they've drawn it in the notes. And there's a reason for this. It's because there's a pretty big difference between the internal nodes in this tree and the leaves in this tree. Internal nodes are all operators. Leaves are all numbers. And that is actually going to play into how we define this binary expression tree. So keep in mind, internal nodes, they are all binary operators, which means all of them have exactly 2 arguments, which means every internal node has exactly 2 children. And every leaf is going to be a number. Now we're going to represent the operations by symbols. So the symbol mark plus, the symbol mark multiply, and so on and so forth. And so we can then define our binary expression tree as either a leaf or an internal node. Since our leaves are numbers, we'll say our binary arithmetic expression is either a number or a binary node. And our binary node is a structure that has 3 parts. The first field is the operator, which is a symbol that is one of these 4. Notice how we are being very precise in the contract here. There is a reason why precision matters with contracts. It's because Racket is not a statically typed language. It's dynamically typed, which means we don't explicitly tell it the types until it's actually being evaluated. And so if you're trying to share this with a user or with another programmer, it's so critical that you give an accurate contract so they know what to expect. What will this function actually work on, and what does it actually produce? So in this case, our binary nodes only work with these 4 values, and then our left and right subtrees are binary expressions. They could be binary nodes or they could be numbers. So we have some examples down here of actually using this. I'm not going to walk through that. And there's another example on the next page of drawing the tree represented by that. And that's actually something that's good practice for you to do, is to take a binary tree or a tree and turn it into the Racket code, and take the Racket code and turn it into the picture of a tree. Sounds like an awful good final exam problem to me. I'm writing your final exam right now. All right. Since we have a data definition, we need to actually create the templates for this. Remember that your template should follow the data definition. We have mutual recursion in the data definition, so we should anticipate mutual recursion in the template. Now, if the expression is a number, we're going to do something with it. You'll note that we're not calling a function on the number because it's just a number. It's boring. If, however, it is a binary expression node, then we're going to call the binary node template. And the binary node template is going to relate the operator in some way to the results of calling the binary expression template on the left and the binary expression template on the right. That's it. So now that we have our data definition and we've seen what these trees look like, we should, do something with this. And the most important thing that you could do with the binary expression tree, of course, is evaluate. So I give you an expression formed as a binary expression tree, and I want you to actually evaluate it. So give me one number that is the result of doing all those operations. So we can take our template and we can fill it in. So we'll call this function eval. And if it's a number, you should just produce the number. 5 is a valid binary expression. 2 is a valid binary expression. If that's your binary expression, you should just produce that value. Otherwise, we're going to call eval by node. So that is going to be our function that's going to evaluate something that is actually an internal node. So that function, what it's going to do is it's going to look at the symbol of the current binary node. And if that symbol is multiplied, we are going to multiply the result of evaluating the left subtree by the result of evaluating the right subtree. And if the operator is add, we are going to add the evaluation of the left subtree to the evaluation of the right subtree. And if it's divide, we're going to divide the left subtree's evaluation by the right subtree's evaluation. Are you getting bored of me saying the same thing? This is really ugly. This is awful. This is terrible. The reason why this is terrible is because we've got all of this repeated code over and over and over again. It's got to be a better way. Of course there is. There's always a better way. By the way, there's like a lot of languages and libraries where the motto is there's more than one way to do it. That might be OpenGL's motto. All right. So what we can do is that solution there. We were given the assignment problem. That's the solution that was splattered out onto paper. That's okay if that's your solution. If you have time, it's more important to us that you have a solution that works than you have a beautiful solution that works. We're not really judging you on, did you give us this God-like solution that's amazing and light shines down from heaven? No, that comes with experience, and every programmer hates every other programmer's code. But if you have time, given the function that we just implemented, you should go back and look at it, and if you have time, ask yourself, can I do better? What ways could I do better? The way that I could do better is I could remove a lot of that repeated code. The process is called refactoring. This is a refactored implementation of the previous code. What we've done is we have abstracted that call to evaluating the left and right subtrees. So now we call eval by node with an operator on a left and right instead of on a by node. And so what's going to happen is we're going to apply the appropriate operator to the left and the right. And then to call eval by node, we pass the operator, and the result we get from evaluating the left subtree and the result we get from evaluating the right subtree. And they're functionally the same. At the end of the day, these two functions both work. But obviously, I like the second solution more. Actually, that's not true. I don't like this one either. It's terrible. Can anyone guess what I don't like about it? Technically, it's a topic we haven't covered yet. Yep. Yep. I can make that simpler, so let's do it. So the thing I don't like about this, and technically speaking, we haven't covered this yet, but I don't care, because I want to show you how beautiful the answer to this could be. I take the symbol and I just replace it with the actual thing. I don't like that. Ugly. Hideous. We have totally ignored one of the beautiful things about Racket and Scheme, which is functions are values. And you can put a function in a list, and you can put it in a field, and we can take advantage of that and make this even prettier. So let's do it. So I have over here the binary node definition, and I have a test, and that's all good. For some reason on there, it looks like it's showing up as pink, meaning I did something wrong, but I didn't. So let's do this function. Now, in order to do this, by the way, you're going to have to up your language level because beginning student with list abbreviations doesn't support this, even though that is actually a part of the full Racket and Scheme language. So we're going to do eval. Now, if the current node is a number, I'm going to produce the number. The base case does not change. Otherwise, Here's where it gets fun. If I can spell, which I usually can't. I'm going to get the operator from the node, and I put it in the position of where my function call would be. If you note, when I made this tree, my operators were not symbols, because functions are values. We will be covering this shortly. But it's cool to see. So I am going to apply my operator for the current node to the result I get from evaluating the left, and the result I get from evaluating the right. Make sure all my brackets match. There we go. Wow, look at that function. I got this answer down in one function, like 1, 2, 3, 4, 5 lines of code, no mutual recursion, no crazy symbol translations. And now you're like, yeah, but does it work? Yes, it does. Isn't that prettier? That's so much simpler. And when we move on to talking about functions as values, you'll realize just how powerful that really is. If a function is a value, then I can write very generic functions. I can write insertion sort once, and it will work on anything. Because I will pass as a parameter the method by which I compare two elements together. Passing the ability to treat functions as values is very, very powerful. And it is a big part of this language. And yes, if you're wondering, you can also do this in C and C++, although it's not as pretty. Yes, you need to upgrade the language. I'm using to do this intermediate student with Lambda. I don't know if you explicitly need the Lambda to do it, but I like Lambda, so I always turn Lambda on. Because for the record, when I learned the language, we learned it from Lambda with Lambda from day one. That's always fun. All right, so there's our very beautiful binary expression tree, which we'll probably cover again when we talk about functions as values. All right, so those were all binary trees. One of the things I want to point out to you is it didn't matter if we were doing an evolution tree or a binary expression tree. Did you notice that the templates and the data definitions pretty much all look the same? And all of the functions to traverse the tree all roughly look the same? It's because they're all binary trees. And so the functions are all going to look roughly the same. Just because we called it something different, just because we have different data types or different names for things, didn't change the basic algorithms that we have for that binary tree. Binary trees are one type of abstract data type. So now let's try to think of things that are different from binary trees, like a general tree. And general trees are everywhere as you look. In Racket, if we actually tried to do binary expression trees on their operators, it wouldn't work. Because add and multiply in Racket actually take more than 2 arguments. So then we start having to ask ourselves, if you have operators that take more than 2 arguments, like these here, what are we going to do? Because our definition of a node, or an internal node, is that it had exactly 2 children. So am I supposed to create a definition for a node which can have 3 children, and then 4 children? What am I going to call them? Left, middle, right? Left, 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 middle, middle, left, or right, middle, right? Like, what am I going to... And what if I have 100 children? What am I going to call them? Your child 0, your child 1. Then the names start to have no meaning whatsoever. So we need some way to create nodes, internal nodes, that can have any number of children. And you know the answer for this. The children are a list. And this is going to get very ugly. So we're going to do this example with Racket's definition for add and multiply, which is they take any number of arguments. And so what we're going to do is we're saying an arithmetic expression now is either a number or one of these arithmetic nodes. And the arithmetic node just has two fields, the operator and the list of children. But this is where it gets ugly. Because not only do we have a mixed data type, so we're going to have mutual recursion because we've got mutual recursion going on here, but wait a minute, I've also got a list in here. So my template is not only going to involve mutual recursion, it's also going to involve recursion on a list. Really ugly. So just so you can see how we would actually create this, there's some few trees here and a few examples of doing this. We've got things like an empty list. List is, I'm not sure what it means. We've got there, and it's got 3 arguments to multiply. We've got 2 arguments to add, and so on and so forth. So fun stuff there. You can play around with it on your own. Here's the template. Remember, I said this is going to get ugly because we've got mutual recursion and we're going to have list recursion going on. So if this is a number, we do something with the number. That base case is still the same. It's not going to change. But if this is an arithmetic expression node, then I need to relate that arithmetic operator not just to my left and right child, because I don't just have a left and right child, I actually now have a list of children. So I'm going to do something with my operator and my list of children. So my list of children template, if I have no children, I'm going to do something. If I'm done processing all my children, we do something. Otherwise, I am going to do something with evaluating my first child and combine the result of evaluating my first child with the result of calling a list of, which is this list template here, on the rest of my children. So this is mutually recursive there, and for the rest of the children, I'll call this function. 2 kinds of fun recursion going on. So you actually, if we were to draw this recursion out, you've got function A and function B, and A calls B and B calls A, and B also calls itself. I didn't say it was pretty. I said it was ugly, and I warned you in advance, this is not pretty. All right. So let's write the evaluation function here. If it's number, produce the number. Base case stays the same. Otherwise, we are going to apply the operator of the current node to the children. And we'll call a children function. The children function is apply. So, in apply, if this is the base case, that is, there are no more children to apply this operator to, the base case is going to depend on what this operator is. So if the operator is add, the base case is 0 because adding 0 does nothing. But if this is multiply, you don't want your base case to be 0 because that would make everything 0. So for multiply, your base case is 1. So that's if there are no more children, adding the base case. Otherwise, if this is an add operator, we are going to add the results of evaluating the first child to applying the operator to the remaining children. And if it's multiply, we're going to multiply the results of evaluating the first child with applying the operator to the remaining children. Nasty little piece of code, isn't it? It's kind of tricky to follow through. So what I want to do is we have a trace, a condensed trace here, and it's kind of hard to follow because we've written this in such a way that you've got like this make AI node, and it gets very hard to trace. So I want to show you an alternate way of tracing this that maybe will help you see what's going on here a little bit better. So I need some space to do this, and I should probably turn a light on. see, where's the lights? So first off, I want to draw this tree we're working with. So I want to go, what is our tree here? I wrote it down so I could see it. So my tree is 3 times 4 plus 2 times 5. There we go, there's my tree. So when I call eval, I'm calling eval on this. And that's going to result, and I check and I say, oh, look, this is not a number. It's an AI node. So now I'm going to call apply on, I'm going to pass plus, and I'm going to call it on my list of children. And my list of children is going to be that. I find it a lot easier to trace these functions, by the way, by replacing all the structure nonsense with an actual picture of the tree you're working with. Because then it's very clear. This is the tree I have. All right. So I'm going to apply a plus to my children here. So the first thing I do is I'm going to evaluate, I'm going to add the result of evaluating my first tree, my first child, to applying plus to my remaining children. There's some number of closing brackets there. Do you see how much more obvious this is as to what's going on when you actually draw the trees themselves? You should do that. All right. So now I'm going to call eval because this is my first argument, and I notice that it is not a value, so I need to call eval on that subtree. So when I call eval on that subtree there, it's going to be like, oh, you're not a number, so it calls apply. So this is going to turn into applying multiply onto that node's children, which are 3 and 4. And so that's going to turn into multiplying results of calling eval on 3, which is the first child, and applying multiply to the next one, the rest of the children. And then if we keep doing this, when we call eval on 3, it just produces 3. Because it's a number, it's base case, we stop. Yay. And then we're going to, now I'm going to do a couple steps in one here because we're running out of space. But now we're going to call apply on multiplying list by 4. And so now we're going to get eval of 4. And we're applying multiply onto, that's the empty list, by the way, quote, bracket empty. This is going to give us 4. I threw the chalk. That's funny. And then when I call apply on multiply with an empty list, it's going to give me 1. And so that first argument is finally going to end up at plus 12. And now we come all the way back up here, and now we're going to apply plus to the list containing the right subtree. Does it make a little more sense when you draw it out with the trees? Yep. I'm not sure about that. I'll have to think about it. More likely than not, I just wouldn't ask a step-up question with a tree in it. Or a tree that's just a list of numbers or something, because you only have so much space, and as I'm sure you all learned from writing code on a piece of paper, it sucks. Because you have to write a lot of stuff that you would just type down in like a fraction of a second. Yeah. So if you continue through here, so all of this that I've drawn here, that's just getting to that step there where we have plus 12. And then we would go through and do the same thing with the right subtree. And again, I can't stress this enough, especially for these tree algorithms. And when we talk about graphs in a little bit, drawing it out and actually tracing the code on the actual picture of the item will be much more useful than trying to use these weird make node crap. Draw it out. Do some experiments. You will understand the algorithms better. If we continue this very long-winded evaluation, we see that this tree should eventually evaluate to 22, which of course you're human and you've been doing math since you were like 4 or maybe earlier. I don't know. You probably looked at this tree and were like, of course the answer is 22. But this is a computer. So. All right, any questions about how this works? All right. And again, if you're wondering, can we apply my lovely trick to this like we did with the other one? Yes, of course you can. This code can be further simplified by doing my fancy little trick of treating the operator as a value, and we'll do that another day. All right. Now, here's the interesting thing. So all of the trees that you've seen so far, we have actually treated the tree nodes as structures if they were internal. So all internal nodes were an actual structure, and then our external nodes were, they might have been a structure or they might have been like a simple data type. You don't have to use structures. And in fact, my entire experience with Scheme, up until I started actually working with this course, which was about 10 years ago, I never used structures because if memory serves me, at the time they didn't even exist in Scheme. Structures are a convenience for you. They really are. And when we showed them to you a few weeks ago, we actually showed you how you would create all of the functions that a structure gives you while still using a list. Realistically, a list could just be, or a structure is just a list with a bunch of functions that are appropriately named to extract, the first element. Oh, that's the name. The second element, instead of saying second, oh, that's your age. They're just creating handy functions for you. What I'm trying to say is there's absolutely no reason that you can't do the problem we just did without structures. You can represent binary trees with lists. You can represent any kind of tree with lists of lists. You can represent trees with arrays, and you can ask Roger all about that. So let's take that data definition from before and let's translate this into something that is equivalent but doesn't actually use a structure. So now we're saying an alternate arithmetic expression. The base case is the same. Base case is a number. Otherwise, it's consing the operator onto a list of arguments, i.e. a list of children. And that list of children, each of those children are going to be alternate arithmetic expressions, which means you're going to end up with a lovely nested list. And you can take this nested list and you can draw a tree from it, and you can take a tree and you can draw a nested list from it. And you can write the same functions we're going to leave the implementation to you as an exercise, you know, that studying thing you're supposed to do. Good study practice. And to be fair, if any of you do actually implement this and you post your solution to Piazza, one of us will let you know whether you've done it right or not. All right. So you can use lists if you want. There are advantages and disadvantages of using lists. A disadvantage is you don't get any of those lovely named functions created for you. So you'll have to create them all yourself. The advantage is because you're just using a standard list, you actually have a lot more flexibility than you would have with a structure. So it is kind of a trade-off. In my own scheme code, I do not use structures. I only use lists. Yeah. All right. Now, this mutual recursion thing, as I said, it's pretty tricky. And it can be very daunting to think about how do I actually solve this. But one of the things I want to reiterate is that that data definition is telling you the answer. The data definition is showing you the pattern of mutual recursion. And it's really important that when you get a data definition that you create that template for. That template is the extra information that the user needs in order to actually, you know, use the thing that you have created. It's that extra information, holding them by the hand and saying, look at my data structure. This is how you use it. And for mutual recursion, it's really important you have this. The best advice that I can give to you is to get some practice. Do some more sample problems. And I have to work on your assignment 8 and, you know, grading your midterm, but I'll try to make some more sample problems for this, because the more you have, the better, right? All right. So what other ways can we use general trees? Well, general trees are actually everywhere. And to be quite honest, these arithmetic expression trees aren't really that useful. There are better ways of doing it. But there's lots of other ways that you can do general trees. A general tree that I like is called the trie, which is a data structure that we use, a general tree. And you can have a trie of words, which is really fun, and it's actually how like autocomplete is done. You start typing something, and the letters you are typing is actually the path through the tree. And then when you stop typing, whatever node you're at, all of the children are all of the possible ways that you can complete what you've already typed. And maybe it's done on a character-by-character basis, or maybe it's a word-by-word one, but you can actually do things like autocomplete and suggest using this general tree known as a trie, which is really, really cool. There are other things which are general trees. Text. A chapter is the root. And a book would be the root, let's be honest. So you've got a book. A book has some number of chapters. Chapters have some number of sections. Sections have some number of paragraphs. Paragraphs have some number of sentences. Sentences have some number of words. Words have some number of characters. That's a general tree to organize a document. We probably wouldn't go down to the word or character base, but you get the idea. A web page is also a general tree. You have a web page. It has things like a title and a paragraph, and paragraphs are made of other things. And you know what this actually looks like? How many of you have heard of something called XML? It's a lot like XML, because guess what? You can take XML and you can turn it into a tree. That's pretty handy. Lots of fun things that you can do. Here's another example of a general tree, and I would like to point out that in computer graphics we use trees all the time, because they're super handy. I could use a tree to describe this room. The root of my tree is room. So this room is, 1056 or something. So room 1056. And inside my room, I have walls. And the walls have a material and a color and so on and so forth. And I have to describe, oh, here's this wall, and here's that wall, and here's the ceiling and the floor. And then I have items in the room. And items in the room is divided into animate and inanimate objects. And inanimate objects, there are desks and chairs. And desks, I would describe the shape of those desks, the positions of those desks, the color of those desks. And the same for chairs. And then for animate objects, I have the actual humans themselves. Or, maybe you're an alien or something. Maybe you're a unicorn in disguise. I don't care. You're some kind of animate object, a robot, maybe. but you have different properties as well. In computer graphics, what I just created for you, it's called a scene graph. It's how we actually describe the contents of a space. And what's interesting is for animated things we have internal skeletons. So the traditional pose for an animated character is this. This is called the T-pose. And every animated thing starts out in the T-pose like this. And then when we want to animate them, we get a guy in a crazy suit to do some dancing or something. But we create an invisible bone structure, and then we're measuring the rotations and translations on each of those bones. Those bones form a general tree, and for a human, the root of the tree is right around the hip area. And then out of that, you have the spinal column coming up, and then you have the actual hips. And the hips have legs, bones, and the hands, of course. You've got the wrist, and from the wrist, then you've got each finger and each joint on each finger. So you can actually create a general tree out of everything. And those skeletons, by the way, we actually use those for all kinds of animation fun things. And it's really cool because in some ways, if I rotate my arm up, it actually impacts all of its children, because they're now all in a different position. Graphic stuff. But anyways. Trees are everywhere. They are very useful data structures. Now, I've already hinted at this, but let's go back and talk about nested lists again. So you may remember you can have lists with lists inside, and those lists have lists inside. That's totally true. A list can technically contain anything you want. It can have lists, it can have anything, including other lists. A nested list can also be a tree. So I can take an empty list, and that's my root node. And a list containing one thing, you can take any list, any nested list, and you can draw a tree that represents that nested list. And vice versa, I can take any tree and draw a nested list that represents that tree. That's kind of cool. And we can create a data definition for this, because we got to create data definitions for everything. So here's our nested list, and we're going to deal with just nested lists of numbers, but in truth it could be a list of anything. So a nested list of numbers is either empty, because empty is still a list, or it's a number added onto a nested list of numbers, or it's a nested list of numbers conned onto a nested list of numbers. And that definition there gives you an arbitrarily nested list. It's great. Maybe a little ugly. I don't want a nested list. It's ugly. It's hideous. I have this tree representation, a nested list of numbers, and it's got all the nesting in it. I just want the numbers. A plain, flat list of numbers. I don't want any nesting. One of the most common mistakes that people make with recursion on lists is they end up producing a list with nests. That is, lists inside of it. So how do we get rid of that list? Well, you could have implemented the function correctly. Or you can implement a list flattener. And a list flattener takes a nested list and it turns it into just a list of num. That is a very useful function. Before we do it though, let's look at a template here. So our nested list template, if we're empty, we're going to do something. Otherwise, we're consing the first item onto doing something with the first of our lists, the remaining list, and the rest of the list. Otherwise, so that's one case, and if the first thing in the list is not a list, then we do something with the first of the list, and we call the recursive function on the rest of the list. This template just followed the data definition exactly. That's all we're doing. If you want to know what is the biggest hint for a data definition, or a template, look at the data definition. Just follow it. So given that, we'll come back to count in a minute. How do we flatten the list? Well, if the list is empty, I produce empty, because that's flat. If the first item of the list is not a list, item onto the results of flattening the rest of the nested list. If, however, this item, the first of my list, is a list itself, then I have to append the results of flattening myself, the first of the list, with the results of flattening the rest of the list. Follows the template, doesn't it? Follows exactly. And we can write all kinds of functions. The function that we had before this was simply to count how many items were in the list. Not how many lists are in the list, how many actual simple items are in there. So if the list is empty, there are 0 items. If this item is not a list, then we add 1 to the count of getting the number of items from the rest. If this item is a list, however, then we add the number of items in the first element to the number of items we get from the rest of the list. 2 functions do fundamentally different things, follow that template exactly. And the template followed the data definition exactly. And we could trace through this. That's fine. And there's a trace here. And it's going to count the items for a nested list that's fairly simple. I'm not going to trace through this for you, but I do recommend you trace through it yourself. All right. So that's kind of it for this section on trees. So we have tracing through it, we have flattening. We are 2 slides ahead of the other class, so I don't want to do any more. I should probably mark that question on your midterm. You should probably go home and eat something. It's cheat night at KFC, right? Yeah, sort of. Anyways, we will review this topic on Thursday's class. Go home, relax, maybe work on assignment 6. See you next term. Well, I don't think they teach this next term, and I'm teaching OS next term.